Hello again. In this video, we're going to go over some examples where we evaluate definite integrals using the substitution method. Okay, so let's look at this definite integral. Now, normally we would evaluate this definite integral using the fundamental theorem of calculus. Remember, as long as this function is continuous from the lower limit to the upper limit, then the fundamental theorem of calculus says that we can evaluate this definite integral by finding any antiderivative of this function and then evaluating it at the upper limit minus what we get at the lower limit. The issue that we run into in this case, though, is that we don't know the antiderivative of this function. Okay, and so we're going to use substitution to find it. Okay, so let's let u be the inner part of this composition. So let's let u be the x plus 3. Okay, and then remember, after you do this, you take the derivative of both sides with respect to x of this equation. Of course, this is going to equal 1, right? The derivative of that with respect to x is 1. And so that basically means du is equal to dx. Just multiply the dx over. Okay, and then we're going to use both of these equations and substitute them back into this definite integral. And remember, the idea in substitution is to try to change the variable of integration from x to another variable, which we're calling u. And hopefully we can find the antiderivative of the new integrand. Okay, so let's see what happens here. So it looks like we get 1 over u cubed, right, since this is equal to u. And then dx and du are the same thing. Okay, so that just becomes du. Then the limits change as well. So that's something to keep in mind. These are the limits when your independent variable is x, your variable of integration is x. But now that you change your variable of integration to u, then the limits change as well. Okay, so to find out what u is, when x is equal to 0, you plug a 0 into here, and notice that you get u is equal to 3. Okay, so that's your new lower limit. And then your upper limit, when x is equal to 2, plug a 2 in, you can see that u is equal to 5. Okay, so if you change your variable here, your limits have to change as well. Okay, so now we're going to try to evaluate this definite integral. Now keep in mind, these are equal, right? So once we know what this definite integral is, once we know what it's equal to, then we're actually finding what this definite integral is equal to. Okay, the good news is we know the antiderivative of this function. Let's just rewrite that as u to the minus 3. Remember, u to the minus 3 is the same as 1 over u cubed. And then we can apply the power rule to find the antiderivative of this. Okay, so it's going to be add 1 to this exponent, so it's going to be u to the negative 2 divided by negative 2 plus any constant. And so that gives you the family of antiderivatives. Then we just need one of them, so let's let c be 0 to make this as simple as possible. Then notice this u to the minus 2 you can write as u squared in the denominator. Okay, and now we just need to evaluate this at the upper limit minus what we get at the lower limit. So f of 5 minus f of 3. Okay, so f of 5, just plug a 5 in, minus what we get when we plug in a 3. So it looks like we get negative 1 over 50. And then notice this is a plus sign. And this appears to be 18, so 1 over 18. Now, we do need a common denominator to add these fractions together. Let me go ahead and factor out what they have in common first. It looks like they have a 2 in common. So I'm going to factor out a 1/2. Okay, and then let's get a common denominator between the 9 and the 25. And so it looks like we need 9 times 25. Okay, which appears to be 225. So that's our least common denominator here. Now, of course, you're going to have to multiply this one by 25 over 25 to get this to be 225, and then this one's going to be, you're going to have to multiply by 9 over 9. Okay, so ultimately, this is going to be negative 9 over 225 plus 25 over 225, and then times this 1/2 in front. Okay, so when you add those together, of course, you get 16 over 225. And then multiply that by the 1/2, and you get 16 over 450. Or actually, you can just cancel the 2's here, right? 16 over 2 gives you 8. And so it reduces to 8 over 225. Okay, so that's what this definite integral is equal to. Now again, the issue in this problem is we had to use substitution to be able to find the antiderivative of this function here. So we turned it into an integral in terms of u, and then we were able to find the antiderivative of the integrand. And remember, you have to change your limits if you change the variable of integration. Okay, so let's try another one. Okay, again, we can use the fundamental theorem of calculus to find this, but we don't know this antiderivative. So let's use substitution and change the integrand. So in this case, let's let u be the x cubed minus 1. Okay, and then let's take the derivative of both sides of this with respect to x. Of course, that gives you 3x squared. And then if you solve for dx, multiply the dx over to the other side, and then divide by this 3x squared. Okay, now let's substitute these back into the original definite integral. So this becomes x squared over u, and then this dx becomes du over 3x squared. Then notice that these x squares cancel out. Okay, and then we got to change our limits. Okay, so remember this is x equal 2 and this is x equals 3. So when we plug a 2 into here, we get 8 minus 1. So that's 7. That's our lower limit. And then when we plug a 3 in, we get 27 minus 1, which is 26. Okay, and let's clean this up a little bit. Notice you have a 1/3 here. When we cancel these out, we are left with a 1 here. So you have a 1/3 that you can factor out of the definite integral. And that leaves you with 1 over u, and that's your new integrand. Okay, so we just now need to find any antiderivative of this. Okay, of course, the antiderivative of 1 over u would be the natural log of the absolute value of u plus any constant. Okay, and so then we're going to evaluate this at the upper limit minus what we get at the lower limit. So it's going to be natural log of 26. Actually, the natural log of the absolute value of 26, but the absolute value of 26 is just 6, or 26. Minus the natural log of the absolute value of 7, which of course is just 7. And then all of that is multiplied by this 1/3. Now keep in mind, we're using 0 here, again, as our constant. Okay, so it looks like you get natural log of 26 minus natural log of 7, all divided by 3. Okay, so that's how you work out that one. All right, let's look at one more. Okay, again, the problem that we run into is that we don't know the antiderivative of this function. Now, this function is continuous on this interval from 0 to pi over 2. So we can use the fundamental theorem of calculus. But the problem is we don't know an antiderivative of this function. Okay, so let's try to use substitution to change this integrand to something that we know the antiderivative of. All right, so in this case, let's let u be sine of x. Okay, now take the derivative of both sides with respect to x. Now remember, the derivative of sine of x is cosine of x. And then when you solve for dx here, multiply the dx to the other side, and then divide by the cosine of x. We get dx is du over cosine of u, or cosine of x. Okay, and then let's just substitute these in. So it looks like this becomes u to the fourth, and then cosine of x, and then this dx becomes du over cosine of x. Of course, these cosine of x's cancel out, and we're left with u to the fourth as our integrand. Okay, but again, we have to change these limits. Okay, so when x is equal to 0, sine of 0 is 0. So our lower limit remains at 0. And then our upper limit, when x is pi over 2, sine of pi over 2 is equal to 1. So that's our new upper limit. Okay, now we just need any antiderivative of u to the fourth, which of course is u to the fifth over 5, plus any constant. And again, we're going to let that constant be 0. And now we're just going to evaluate this at the upper limit minus the lower limit, so it's f of 1 minus f of 0. Now f of 1 gives us 1/5. Of course, f of 0 is just 0. Okay, and that leaves us with 1/5. Okay, so those are 3 examples of where you can use substitution to evaluate definite integrals. Just remember that if you do that, you do have to change the limits. Okay, so sometimes people forget to change their limits. If you were to evaluate this from 0 to pi over 2 and not change your limits, then of course you would not get the correct answer. Okay, so I hope you found this video helpful. Thank you for watching. Bye.